Good afternoon. Today what we're going to do in Foundations 30 is take a look at Chapter 5 on probability. Probability is a situation that we have looked at in many aspects of our life. Predicting weather is one example. When we talk about 60% chance of rain, that is talking about the likelihood that it's going to rain. And that is what probability is all about. So today what we're going to do is we're going to look at some situations and how we can calculate the probability of an event occurring. So here is one situation. Jack and Jill are playing a game. They roll 2 standard dice and determine the difference between the numbers rolled. Usually when we play dice, we add the numbers. Well, in this situation, we're going to subtract. So, for example, if we roll a 6 and a 5, we subtract and we get a difference of 1. And so how many differences are possible? 6 minus 5, getting a difference of 1 is a possibility. What if it was, where's my pen here? What if it was 6 take away 4? We would have a difference of 2. 6 take away 3, for example, would be a difference of 3. If we had 5 take away 1, we would have a difference of 4. If we rolled snake eyes, 1 take away 1, we would have a difference of 0. And if we had 6, let's say, take away 1, we could have a difference of 5. I think that no matter which way we roll the dice, we are only going to see differences of 0, 1, 2, 3, 4, or 5. So those are all the possibilities. And of course, we can get some of these differences in more ways than just what I've indicated. So the questions that follow here are asking us to do a prediction. Which difference do you think is going to occur the most often? Whoops. And in my class, I often ask my students, based on just what they understand about dice, what difference do they think is going to occur most often? Which difference will occur the least often? And which differences will occur equally often? And if you played with dice and you're used to adding them together, you may have an idea of what would occur most often for the sum, but the difference may be something different. So what I often do in my classes, I get them to do some experiments, and I have them do this activity. Where the partner roll 2 dice 36 times, record the difference each time as a positive value, and how closely do the results match your predictions. So I would have them do something like this, where they would, I'm going to get these to roll here, hang on a second, that's being, I got to delete that little dot there. Okay, so roll a dice, 3 take away 2, would be a difference of 1. Roll those dice again. 6 take away 4 would be a difference of 2. And so just tally up and keep track of what your differences are as you roll the dice 36 times. Now that will produce some trial and some experimental results, which would help in terms of determining the experimental probability for each difference as a fraction. So experimental probability of an event is represented by this notation. The probability, P, A represents the event that you are focusing on. N, A is the number of times the event occurs, and we've seen that notation before, the N counting the number of times an event occurs. NT is the total number of trials in the experiment. So just based even on the 2 rolls, we could talk about what's the probability of getting a difference of 1. That means that we would count the number of times that a difference of 1 occurred over the total number of trials that we conducted. Well, as it turned out, I only rolled it twice, and 1 out of the 2 times we had a difference of 1. Now, is this something that is true, that we would always end up with 0.5, which would be equivalent to 50% of the time you're going to roll a difference of 1? No. Based on the 2 trials that we ran, it's not really very, indicative of what would happen over many trials. So experimental probability is based on the experiments that you conduct. but it's not necessarily what should happen in a perfect world. And that's where we would lean more towards what's called theoretical probability. So this outcome table is an opportunity to figure out exactly all the differences that are possible, not just me kind of listing a few. So for example, if you rolled snake eyes, 2 ones, the difference would be 0, a 2 and a 1, a 3 and a 1, a 4 and a 1 as they've indicated. And so what you would do is go through and record all the different possible sums. So there's more than one way to get a difference of 1. There's more than one way to get a difference of 0. And so therefore you would complete your outcome table, and I'm just going to take a quick minute to plug all of these differences in. There we go. Quickly doing this, because when we're going to talk about theoretical probability, this represents all the possibilities of what should happen in a perfect world, not based on what has happened in our experiments. And so once we end up filling in the outcome table, you're going to see very quickly that when we roll 2 6-sided die, that there are 36 possible outcomes. 36 possible differences. And I'm just about done here, so I have them all. So now it says determine the theoretical probability for each difference as a fraction, and how does it represent, or how closely, to the experimental probability. Now, I didn't have much of an experimental probability, but I did talk about the probability of rolling a difference of 1. Now, to get theoretical probability, we're talking about the number of ways of the event can occur over n of s, which stands for the total number of outcomes in the sample space. We just drew in that there are 36 different possible outcomes. So the number of times that we see 1 occur in the possible outcomes over the entire sample space. What we have here is that 1 occurs 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I better make sure I got them all here. Hang on a second here. I better do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways that a 1 can show up when we're talking about the difference. So there was 10 ways out of the possible 36. It asked us to write this as a fraction. When you compare 10 over 36 to my 1/2, those are not close. In fact, if I turn 10 out of 36 into a decimal, just doing it on my calculator here, what we end up with is 0.27 repeating, which is approximately 27.8% of the time, you would get a 1 theoretically as a difference. That's not very close to a probability of 50%. So our theoretical probability is what we're going to focus on most in Chapter 5, and the experiments less likely. So let's take a look at what kind of information do we need to know about these probabilities. So first of all, an event is a collection of outcomes that satisfy a specific condition. That would be like the event of getting a difference of 1. For example, throwing a standard die, throwing an odd number. Could be a collection of outcomes like getting a 1, 3, and a 5. Now, it's important for us to understand what kind of answers that we're going to get. Probability of an event can range from 0, which it means it's impossible to happen, there's no chance it's going to happen, to 1, which is a certainty, it's guaranteed to happen. And your answers can be written as a fraction, as we've seen, a decimal, and a percent. So all of our answers, as we write these probability answers, are going to be a fraction or decimal between 0 and 1, as a percent from 0 to 100%. Those are the types of answers that we are going to see in Chapter 5. So part of probability is making sure that items have an likely chance, an equally likely chance of occurring. And that is what is necessary for what we call a fair game. If we're going to play a game, we have to have equal chances of winning. And so Sasha and Micah have to invent a fair game as a project. And this is the game that Sasha comes up with. 2 people play, each player has a container. Both players put 3 identical slips of paper, numbered 1, 2, 3, into their container. The way the game continues is that for each turn, both players are going to draw 1 slip of paper from their container. Player 1 will score a point if the product, multiplying the 2 numbers together, drawn is less than the sum of those 2 numbers. Player 2 is going to get a point if the product of the numbers drawn is greater than their sum. And neither player gets a point if the product and the sum are equal. After each turn, they return the slips of paper to their container, and the game consists of 10 turns. So our goal is, does player 1 and player 2 have an equal chance of gaining a point? So to see how this game works, what we're going to do is try it right here. So I have a couple of spinners that are going to pop up. Here we go. They're going to represent the papers that one person is going to draw from their bucket. So I'm going to do that. The other person draws a number, and they pull out a 1 and a 2. So to determine who gets the point, again, player 1 gets the point if the product is less than the sum. 2 times 1, multiplying our numbers, is 2. Whereas the sum is 3. So the product, in this case, 2, is less than the sum, which is 3. So player 1 gets the point. So I'm just going to tally up that player 1 gets the first point. Let's try this again. A 3 and a 1. The product is 3, whereas the sum is 4. The product is less than the sum. Player 1 gets a point again. Let's try that again. This time a 3 and a 2. The product is 6 and the sum is only 5. So this time around the product is greater than the sum. So player 2 gets a point that time. We'll do one more. A 1 and a 1. Product is only 1, whereas the sum is 2. That means that player 1 gets a point. So based on our 4 trials, it looks like either player 1 is just luckier than player 2, or is it unfair in player 1's advantage? Well, we wouldn't really be able to tell from this experiment, the trial of trying the game. Let's actually try this theoretically. Okay, so is Sasha's game a good way to decide if it's fair, if we're just playing the game? Micah says that you have to use theoretical probability to determine if the game is fair. Well, let's take a look at the theoretical probability. So I'm going to do an outcome table as a way of looking at all the possible outcomes for this game. So an outcome table again is going to allow us to see what happens when we get a 1, 2, or a 3 drawn from one player and a 1, 2, or 3 drawn from the other player. So just completing my table. And again, the rules is if the product is less than the sum, player 1 gets a point. So a product of 1 as compared to a sum of 2, player 1 would get a point because the product is less. A 2 times a 1, the product is only 2, the sum is 3, player 1 would get a point. 1 and 3, we had that one happen, and player 1 got the point for that. A 2 and a 1, of course, is the same regardless, so I'm just going to put player 1 here and here. Now what happens if we get a 2 and a 2? Product is 2, and the product is 4. 2 times 2 is 4, and the sum is also 4. So no player gets a point when the sum and the product are the same. Now we had 3 and a 2 come up. The product was greater than the sum, so player 2 got a point. 3 and 2, that would be the same thing. And lastly, 3 and 3. The product is 9, the sum is only 6. So player 2 would get a point there as well. There is our outcome table. So what is the probability of player 1 getting a point? Well, the number of ways that player 1 can get a point is 1, 2, 3, 4, 5 ways out of the 9 possible outcomes that you can have. Whereas player 2, the probability of player 2 getting a point is 1, 2, 3 ways out of a possible 9. And so using the theoretical probability, it seems like player 1 has an advantage. They can gain a point more times than player 2. So we would have to say that this is unfair, that player 1 has an advantage. So we would have to readjust the game, change it in some way to make it a fair game. So that's the type of thing that we're going to look at in section 5.1 of Foundations 30. We'll talk a little bit about experimental probability, what theoretical probability looks like, as well as how we can notate the way that we would like our probability values to look as either fractions, decimals, or as a percent. That's all for today. Have a good day.